Hello. Today, we will be learning about polynomials. I'm going to assume that you already, and some of tricks regarding the roots of polynomials. I'm assuming that you already know what a polynomial is and how to add and subtract polynomials. However, did you know you could also multiply and divide polynomials? Actually, yeah. Yeah, you probably do. Alright, so actually for multiplying polynomials, you probably already know FOIL, and the distributive property. But let's go over an example of dividing polynomial. Let's say we had the polynomial. Let's do a simple example. Let's say we have a polynomial x squared plus 3x plus 2. I already know the factors of this polynomial. However, let's say I want to divide this polynomial by x plus 1. So, just like in long division, I would want to find the largest multiple of x plus 1 I can subtract from this. So that will turn out to be x. So I subtract x squared plus x. It's x times the divisor. And I'll end up with 2x plus 2. And then I can also subtract 2, minus 2x plus 2, and then this will just be a 0. So as you can see, this is the result of dividing a polynomial, and the remainder is equal to 0. So this is a quotient. This is a quotient. Alright. Let's do a different. Okay, so I hope that helps you understand how to divide polynomials. Here's a really shortcut method for dividing polynomials called synthetic division. So, in synthetic division, instead of writing the whole number, we just write the coefficients. And we take the root of the divide. And we can only use synthetic division if the divisor is in the form x plus a, where a is some integer. Oh, wait, no, where a can also be part of the quotient domain. Sorry. Or the rational domain. Sorry. Alright, let's try this again. So, if you have a polynomial in the form, the divisor is in the form x minus a, the tricky part is that you will put divide by plus a, and in this case a is equal to negative 1. Now, here's a trick for synthetic division. You simply move the starting coefficient down, and you add the highest multiple and to get the next coefficient of the quotient, you want to multiply negative 1 times 1, so and add that to the next one. So that will become 1, 2, and then you want to add negative 1 times 2, which is minus 2. This will be 0. So what you're left with is x plus 2 as desired. So, I hope you get that out of the way. So, now you know how to divide polynomials. Alright, so in a lot of questions regarding polynomials, you want to find the roots of it, which is when the polynomial, let's just call it p of x, is equal to 0. And the root is the x value. So one method to use that you can use to find the root is the rational root theorem. So here's what the rational root theorem states. Let's say we have a polynomial let's just call it f of x, which is equal to an times x to the nth power, where an is some coefficient, plus an minus 1 times x to the nth minus 1 power, all the way to plus a0, or a naught. If one of the roots x is part of the rational number system, then x will have to be in the form p divided by q, where p divides a naught evenly, and q is an integer which divides an evenly. So let's do an example with this. Let's say I want to find the roots of x to the third minus 6x squared plus 11x minus 6. Oh, this looks like a pretty scary polynomial. But remember our tricks. So a0 is negative 6, while an is just 1. So if let's say there's a root that can be expressed as p over q, this would the numbers which divide can divide negative 6 are evenly are just 1, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And the only number for q is plus or minus 1. So thus the possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, or plus or minus 6. Sorry about that. Let's try some of these. Let's start with an easy one, just 1. So if we plug it 1 in, we'll end up with 1 minus 6. Plus 11 minus 6. This is not a root. Wait. Actually, no, this is a root. Sorry about that. Which is equal to 0. So that means that this function, or this polynomial, x to the third minus 6x squared plus 11x minus 6 can be rewritten as x minus 1, since 1 is a root, times some other polynomial. Let's just call this q of x as a quotient. So remembering our division, we can divide both sides by x minus 1, and we divide x to the third minus 6x squared plus 11x minus 6 x minus 1 q of x. We will have to find the roots of q of x. So x squared plus 1 plus x squared. You're left with negative 5x plus 11x minus 6. So minus 5x. We will add we will have to add 5x times the or we will have to add negative 5x times we will have to subtract negative 5x times x minus 1. So plus 5x minus 5 plus 5x squared minus 5x. We'll end up with 6x minus 6, and we can subtract 6 times the divisor. And if we look at this quadratic, we can recognize that this quadratic can be further factored into plus 6. This quadratic can be further factored into x minus 3 times x minus 2. Another thing I forgot to mention at the beginning of the video is I expect you to know how to use a quadratic formula and factor quadratics. I'm going to assume that you know that. And earlier, one of the other factors is x minus 1. So I've come to the conclusion that the three roots are 1, 2, and 3, which satisfy the rational root theorem and this equation. Right, moving on. Okay, so the rational root theorem seemed pretty tricky. However, there is a proof to it. So let's plug it. Let's write the general form of a polynomial. Sorry about f of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus plus a0. So let's say there is some rational root p over q. So let's plug in p over q for f, and this will, rewriting this will allow us to end up with x n q over q to the nth power all the way to a naught. And this is equal to 0. We can multiply both sides by q to the nth power, and we'll end up with an p to the n plus plus a naught q to the nth, which is equal to 0. So if we look at this equation modulo p, we notice that all the terms cancel out except for a naught. So a naught q to the nth is congruent to 0 mod p. And assuming that p and q are relatively prime, that means that a naught has to be congruent to 0 mod p, which means that a naught or p divides a naught. Okay, the same thing can be done with q by taking this equation up here, mod q instead of mod p. Moving on. So that's the main idea of how to find. That's one of the main idea of how to find roots. Another case is with complex roots, and if you remember in the quadratic equation, x is equal to some number a plus or minus some a square root of some number b over c, some number c. This means that if a over c plus square root of b over c is a factor, then a over c minus b square root of b over c, or the conjugate of this, is also a root. A root of the polynomial. Same thing can be said with complex numbers in general. So let's say f of z has a complex root, which is why we're denoting the variable as z, which is equal to an z to the n all the way to a naught, which is equal to 0. So if we apply the complex conjugate on both sides, and I'm assuming that you know about the arithmetic of complex numbers, we'll end up with an z, the conjugate of z to the n, plus dot a naught. And oh, by the way, we're using real coefficients, so the conjugate is still a real number. The complex conjugate is still a real number, and a complex conjugate of 0 is still 0. So based on this, we can see that if z is a root, then if z is a root of the polynomial, then the complex conjugate of a complex number z is also a root of the polynomial. Okay. Next, we will move on to the Vieta's formula. So, as you know, let's say we have a and to do this, before I move on to the Vieta's relations, I want to add another definition. Let's say f of x can be equal to an x to the nth all the way to a naught, where an is not equal to 0. We define the degree of f as the highest power of the variable. So the degree of f in this case is equal to n. The highest power of a variable is the degree. Right, so counting with multiplicity, meaning that let's say there's a double root at a point. The number of roots counting with multiplicity is equal to n for any function with a degree n. for any polynomial with a degree n. So that means that f of x can be rewritten as x minus r1 for one of the roots, x minus r2 all the way to x minus rn for n roots. Because if you plug in any root into this, it will become 0 times some coefficient an. Let us assume that this but for the relations, we must assume that we must assume that the polynomial is monic, meaning that the coefficient of the nth term of the first term is 1. So here's something interesting to notice. If we expand the factorization, we'll end up with f of x is equal to x to the nth minus the sum of all the roots, r1 plus all the way to rn x to the nth minus 1. Because if you want x to the nth minus 1, you must select an x from each one of these factors except one of them. So going through all of that, we will end up with the coefficients of the sum of roots. So the coefficient in front of the second term of a monic polynomial is the sum of the roots. Next, for x to the nth minus 2, the coefficient, we'll select 2 random roots, and each root has a negative sign, so then those negatives will cancel out, which is why I'm leaving a positive in front. So it'll be r1, r2, all the way to rn, the sum of rn, r2, all the way to rn times, let's just say rn minus 1. So the sum of all the possible combinations of 2 roots, there will be n choose 2 roots. If you already know about combinatorics, there will be n over n to 2 of these terms that will be summed up. So the last key information is that the last term is either plus or minus, depending on whether n is odd or even, the product of all the roots, r1, r2, multiplied all the way to rn. Okay, so that's the Vieta's relations of how the roots relate to the coefficients. So, the last thing we are going to, second to last thing we are going to work at, I'm going to look at is transforming roots. Oh, wait. Silly of me, I forgot to do an example relating to Vieta's formulas, or Vieta's relations. Let's say we have some